so we're gonna get going. If you can find your seats. So we're gonna, excuse me, we're gonna start off with a few administrative items. All right. So if everybody could quiet down and sit down, I would appreciate it. Okay, thank you. Okay, a few administrative items. So this is the week where you are in teams. You'll be in teams for the rest of the course. If you're already in a team of 3, we're shortly, hopefully by the end of the day, going to post who is your CI, who is your TA, and where will you meet them. What is the meeting room where you're going to meet your CI this week, and what's the lab room where you're going to meet your TA all semester. In your tutorial, so you're going to go to the lab this week, you're going to meet with your own TA. You are going, in the first hour of your tutorial, you're going to go meet your CI. And with your CI and your team, you will choose a meeting time for the rest of the semester. Okay, so where will you meet with your CI? Well, we're going to do 2 things. We're going to post it on Quarkus, and your CI is going to email you. Pay attention to that email. That's going to say, where do you go this week in your tutorial? That logistics of getting set up with your CI is only going to take the first hour of the tutorial. For the second hour of the tutorial, we will have another coding tutorial. So you go to your regular tutorial room, whatever it is, and we'll spend that hour doing a walkthrough of milestone1, which has just been released. So we'll show you how to write one of the functions in milestone1, so you for sure should get that one right, and how to attack this milestone, because it might be a little more complicated than some of the typical labs you've done up to this point. If you're not in a team of 3, you will meet Dr. Chong in the first hour of your tutorial this week. He's going to group unpaired students, and he's going to complete teams of 2. So if you are a team of 2, you will also go to meet Dr. Chong. On Wednesday, that'll be in My Hall 360. On Thursday, My Hall 320. Friday, My Hall 360. Okay, so he'll take all the students who aren't in teams of 3 and do some kind of team-based speed dating to figure out who goes where. Alan, anything you'd like to add to that?
No, just make sure you know where you're going. We'll post it and repeat like several places to make sure that you do. So I'll see you on your tutorial then.
Not being able to find the room where you get into a team is bad, right? That like makes you one of the very, very last people who doesn't have a team, which you don't want to be. So if you don't have a team yet, make sure you go and meet with Dr. Chong that first hour of your tutorial. Okay, so milestone1 has just been released. You're going to complete it with your team. You're going to submit it by Saturday, February 10th at midnight. It's worth 10% of your final mark. 7% of that is auto-graded. So you pass or fail a variety of tests, and you can run the public tests using ece297 exercise. We also have some private tests which are no harder. They're similar, just to make sure you didn't hard code answers, etc. And you paid attention to the corner cases that we told you about in the header files. So we are going to leave a few things, a few details out of the public test to see, did you actually read the specification that we carefully wrote in the header file? And whenever you don't read it, it makes us sad. So go read it. Half of these tests are approximately going to test functionality, so did you get the right answer? And about half of them are going to test, are you fast enough? We want your API to be quick. 3% of your final grade will be graded by your TA, and it's a more qualitative grade. And there's a rubric on Quarkus that tells you what is your TA looking for. So he or she is looking for project management. Very soon, you're going to get a wiki page assigned to your team. You will track your project management there. We'll talk about expectations. Your TA will talk about expectations. Also going to track your coding style. So is your code clean? Not only does it work, but basically, is it well written? Is it maintainable? We'll talk in lecture about some rules for that. How well did you use Git? Did you do everything in one chaotic commit at the very end? That's bad. Do a bunch of little commits. Some work by each team member, good status messages. And do you know the code? So you can go look for more details in the rubric, which is on Quarkus. Any questions on logistics? Because after that, I'm going to go into like some of the technical information you need to attack milestone 1. All right, sounds like everybody's good with logistics. So I'm going to give you a quick overview of the data and the APIs that you're going to use in this project. Okay, so we're using real data of a variety of cities around the world that come from an organization called OpenStreetMap. OpenStreetMap is an open geographic database of the world. So it's created by regular people all around the world who just contribute information. They like mapping things and entering the data, and there's a lot of data that they've collected. And actually you'll see various websites and programs that have little copyright OpenStreetMap or acknowledgement OpenStreetMap. This data is used for a lot of open source and commercial endeavors. Okay, so how does OpenStreetMap organize its data? So I'm going to tell you first what kind of the raw data looks like. And you're going to work with that raw data a little bit, but you'll often also work with some data that we've processed a bit more. So the raw OpenStreetMap data has 3 types of what are called entities. You know, entity just means class of thing. Now each of these entities, objects basically, is given a globally unique 64-bit integer ID, which is called an OSM ID. Okay, so what do I mean by globally unique? I mean that 64-bit integer is never reused anywhere in the world. This will uniquely identify, for example, my hall, right? My hall building, there's an OSM ID for it. That will have an integer ID that no other object anywhere in this database, anywhere in the world would use. So what are these 3? So that's kind of the key way that you identify something in this database. This was the 64-bit integer. The 3 types of entities are OSM nodes, and OSM node's kind of the simplest. An OSM node is just a point on the surface of the Earth. So it's a latitude and longitude. And they can also attach some data to it. So key value pairs can be attached to it. Building on that, OSM ways are a little bit more complicated. They are a list of these OSM nodes. They're a list of points in order. And if you follow those points in order, it will trace some path. Okay, and that path could be many different things. It could be a piece of a road, it could be a part of a shoreline, it could be a park boundary, it could be part of the outline of a pond. It's many, many different things, but they're all paths. And then the last type of entity in OSM are called relations, and relations group multiple other entities. Okay, so they're a little more free-form. It's just a grouping of other stuff. For example, when later on in this project, you may choose to draw subway lines, right? So not this milestone, but the next milestone, you actually visualize these maps. Many teams decided it would be nice to show subways. And subways are represented as OSM relations, because it groups together a bunch of different things that together, well, nodes and ways that together form a subway line. So that's an example of an OSM relation. Okay, I guess I already mentioned this. All 3 of these things, optionally, can have what they call tags. And tags are key value pairs. So for example, we could have an OSM way, right? Remember that's a path, that has name, a key of name, and a value of Yonge. So that's telling us, hey, this thing is part of Yonge Street. We also could have, on a different OSM way, a key of natural and a value of water. And that might be defining part of a pond, for example. Okay, so all of this is documented on OpenStreetMap's wiki page. So you're going to use wiki, which is an easy to edit web page, to track your project status. It's used by a lot of open source projects as well. So that's actually how OpenStreetMap keeps its documentation. So you go to this wiki and you can see a long list of all the keys that they support. So there's many different questions you could ask about these OSM nodes and OSM ways, not just what is your name and if you're a natural feature, what kind are you? Okay, so a lot of data. So you can download this data for the whole planet, and it keeps getting bigger, but it's now in the multiple terabytes. So it's, last time I checked, which is a couple of years ago, it was already greater than a terabyte, and as people enter more data, it keeps getting bigger. It's hard to work with a file that big, right? You can't open it in a text editor. Text editor will crash. It might fill your hard disk. So what we've done to make this easier to work with is we've already downloaded what are called extracts. Extracts are we've taken the data for individual cities and put them in files. So you don't have to work with this giant file for the whole planet. So this, for example, and you can look at these, right? So in the milestone1 handout, it tells you where they are. So if you actually want to go look at these files, you can. This would be the file for Toronto. And it's still big, still a gigabyte. It's human readable. And you can see it says things like, here's a node. So I told you they're OSM nodes, which are points on the surface of the Earth. It's got an ID, so this big, long integer. It tells you its latitude and its longitude, and so on, okay? This next thing is a way, so this is a path, and we can see that this particular path, this way, has a tag equal to highway, so it tells us it's part of a road. Okay, so the positive of this data is it's powerful. There's a lot of data and there's few restrictions. You can describe those three simple concepts, nodes, ways, and entities, they describe the whole planet with. So not very many restrictions. The XML file that I just showed you is text. It's human readable. So that's actually nice too. You can look at it. The negative though is this data is pretty low level. You know, you didn't look at it for very long there, but there's a lot of data there and it can be a little hard to interpret what does it mean. It can also be a little bit inconsistent. So there aren't that many rules on these names and these tags. It's entered by volunteers around the world. Some of them might interpret guidelines even a bit differently from each other. It's big, as I said, so even for just one city like Toronto, it's a gigabyte. And text files like XML are nice for humans because you can read them, but it takes a reasonable amount of work for a computer to actually go through and figure out what does this mean. It has to interpret, okay, this is a node, this is a way. It has to actually parse through all this text. And that makes it somewhat slow to load. So Toronto, just to load this file and interpret what it means takes our code 45 seconds, which is going to make your map a bit slow to load. So what we've done is you can look at the raw files just if you want to, but you don't have to. That's for you as a human. Your program's not going to use those XML files. We've already done some processing on them. So we wrote a program called OSM to bin, and it reads in that raw OSM data. It applies consistency checks, so things we don't like, we clean the data up. It organizes the data to make it easier to work with. And then it writes out the essential data, the data that we need for this course in the exact binary form that is needed to load basically our objects, our C++ objects, that allow you to ask questions about these cities. So that basically are part of our API, our application programming interface you could talk to. These files are smaller. So we make two files. They end in .bin to denote that they're binary, so you can't read them. They're just ones and zeros. So one of those two files, the one that you need the most, because it gives the most organized view of the data, it's smaller. It's 93 megabytes instead of a gigabyte. So we've kind of squeezed it down by making it binary, taking out non-essential information. And it's much easier for us to essentially parse, right? The XML, we had to have code that goes through and interprets what is this character, what is that character, what is this word. This binary data is exactly what we need to basically populate a bunch of C++ classes. So it goes in much faster. So this particular file takes about a second to load in for Toronto, so 45 times faster. Okay, this is a general technique. You're not going to do it in this course, you're just using it. It's called class serialization. So class serialization means I've got a bunch of data in memory in my classes. I would like to write it out to disk so that I can keep it around and I could reload it into my classes quickly, you know, in the future, maybe the next time you run the program. So this happens so often it's given a name, class serialization. You could try to do this by hand. You don't want to do that. We use a library called Boost Serialization. So there are libraries for serialization. We're using one of them. And basically what those libraries do is if you can get the data inside memory in your classes, and we can do that. We wrote that OSM to bin program, which can read the XML and interpret it. Once you've done that, you can call this library and say, write out all the data in these classes to disk, and then the next time you run the program, you can call that same library saying, read it all in from disk. Okay, it doesn't do really error checking or interpretation, it's just fast. Okay, so hopefully that's all clear. All of this is just for background, right? We've done this, you don't have to write this. So, milestone 1 is all about API layers. So we've got this XML human readable file for Toronto called toronto.osm, OpenStreetMap. We have written this program, OSM to bin, and we've already run it, and we've created 2 output files, okay? This toronto.streets.bin is essentially the more organized data. I'm going to spend most of my time talking about the functions that answer questions on this file. It basically has organized Toronto into streets and intersections and natural features, things that are kind of easier to understand and work with. We also have this file, toronto.osm.bin, which is basically pretty much all the data from OSM that you could ever want. So we've only taken out stuff that we're sure nobody would ever want. And it's organized in that lower level way. So it has OSM nodes, it has OSM ways, it has OSM entities. So it has more information than is in this file, which you will occasionally need. And it's a little bit lower level because of that. Okay, so these are binary files. You're not going to go parse these files. What you're going to do is you're going to talk to header files that we wrote, okay? And there's one header file for each of them. Those header files give you the interface to a set of functions, an application programming interface that we wrote that can answer questions based on what's in these files. And again, this is a standard technique. We don't want to have programmers off trying to parse these files. We build an API so you can ask them questions. So most of what you need to do in milestone 1, and actually the other milestones as well, you're going to ask questions that go through this header file, Streets Database API. So the kind of little bit higher level API. But to get you used to the raw data, we also have 2 functions in milestone 1 that will require you to talk to this other API. So you won't work with it as much, but you have to understand some of it. Okay, that's what we're giving you. What do you have to do? You have to write, well, we also give you a header file called m1.h. You can't change it, it's read-only. This is the specification of what you have to write for milestone 1. In milestone 1, you are writing an even higher level API. Okay, so higher level means kind of easier to use, gives more functionality. So we give you the header file which says these are what your functions have to do. You now need to write those functions. So you can write them in as many C++ files as you want. Often you might call it m1.cpp, but you can make helper.cpp, bob.cpp, whatever. Make as many C++ files as you want. They're all going to go in a directory in your project. And this directory will be set up for you when you initialize the project. And the instructions tell you how to do that. And the way you're going to make this work is basically we're going to test your API by making function calls, and those function calls are all documented in the header file. Until you write the C++ code, none of those function calls will work, right? There's nothing backing them up. We're going to call you and check if you answer our questions correctly. And the way you're going to answer those questions is you're going to call functions in our 2 APIs. Okay, again, mostly in this one, Streets Database API.h. Everything makes sense so far? Yeah, so I'm going to go to A09. Let me clear this. Go ahead. You have to get close to the mic, though.
Okay, is this close enough?
I'm not sure. Okay, we'll see if people can hear you. Speak loudly and get close.
Is this close enough?
Go for it.
My question is, for milestone 1, we're completing the m1.h file, so we're doing a header file, and we're given the CPP files.
No, you are given this header file, okay? And we make it read-only so that you don't change it.
Okay.
You can't change it because that's the specification. That's what we're going to test. If you change it, you have completely messed yourself up. So we made it read-only to say don't change it. These C++ files do not exist yet. Okay? You will make those C++ files so that you actually implement the functions we asked for. Okay? And we're going to automatically test your program to make sure that they actually work.
Okay, and the other .h files, we will use them, right? Like
these two we give you as well. Okay, those ones, we've written those .h files. .h files are essentially the documentation of an interface. So those are two interfaces we've given you to interact with the map data. You know, one a bit higher level, one a bit lower level. And we've written all the C++ that goes behind them, right? You ask them a question, they will answer, and they will answer correctly, or myself and the head TAs are in big trouble, we'll have a late night, okay? But I'm pretty confident they'll answer correctly.
Okay, thank you.
Does that make sense? Okay, so I want to describe what are these APIs you're going to talk to. And I'm not going to go through every detail, I'm just going to give you an overview. You have to read the milestone1 instructions. And the milestone1 instructions include these header files. The header files are heavily commented, they document themselves. Okay, so first a bit of an overview. Milestone1, you are writing a higher level API. So you're building on top of our two low level APIs, you're building a higher one. And here's an example of one of the functions that you might have to write with a comment saying what it should do. Just so you know what's coming, these functions that you're writing are not going to be thrown away. Some of them, at least, you will build on in your later milestones. So it's a good idea to write them with some comments in a way where you think they're maintainable. First, it's going to get you better marks from the TA. Secondly, it's going to make it easier for you in later milestones. So in milestone 2, you're going to use these functions and some other ones to visualize these maps, so build an interactive graphics representation. And in milestone 3 and 4, you'll write some algorithms. Okay, so let's talk about how we're representing this data and how you're going to talk to these APIs. Okay, so how are we going to represent a street map? And the fundamental way we represent it is as a graph. Who here has heard of a graph? Okay, so a reasonable number of people have heard of graphs. Is it just something you heard of in a course, or you heard of it just outside? Maybe that's too vague. Nobody knows who I'm asking. We'll just move on then. Okay, so some people know this, but not everybody. So a graph represents connectivity between items. And it basically has two components. One component are called the vertices, or sometimes called the nodes. They mean the same thing. And we often refer to them as a set V. The other component of the graph are the connections between these nodes, or the edges. And we often refer to that as a set E. And the entire graph, therefore, we can call the set V and E together. Okay, so it just means the nodes and the edges are connections between them. Okay, so you've already used graphs, maybe without knowing it. So a linked list is a form of a graph. Okay, in a linked list, you have a node here, and it has a next pointer to the next node, and a next pointer to, whoops, this is hard to write on. Okay, and a next pointer to the next node. Let's see if I can write on this properly. And so on. Okay? So these circles, the arrows are edges, the circles are nodes. So, and that would be a singly linked list. If you do a doubly linked list, which is a little more common, you have previous edges too. Whoops. All right, so my writing is not working so well on this one today. There we go. Okay, so I finally drawn in my linked list. So doubly linked list with previous pointers and next pointers looks like this. You have at most 2 edges per node, and they form a chain. That's a linked list. A linked list is a special case of a graph. You've also learned about binary search trees. Okay, so a binary search tree, we have the root of the tree, and we can have up to 2 children. So we can have a left child and we can have a right child. So we have these edges. Let's see. I think I'm going to get my surface going for the next lecture. Whoops. So let's see if I can write on this better. Okay, you hopefully get the idea. That's a very poorly drawn binary search tree, but a binary search tree is another special case. So you can have at most 2 children of any node. And those children can be drawn just as you have edges to them. Okay, I guess technically this binary search tree, if it ends there, I might have a child on this side. Okay, so in a binary search tree, every node has at most 2 edges going out of it, right? So it might have no children, so there's 0 edges going out of it. It might have 1 child, or it might have 2 children, but it'll never have more than that. So this is another special case of a graph. Does that make sense? So you know some about these already. In a general graph, you can have an arbitrary number of edges at a node. Okay, so both of those graphs, it was, well, linked list, it was always 2, and binary search tree was up to 2, but a graph kind of has, in general, doesn't have a lot of rules, right? So I can have this node, it can have an edge to another node, that can have an edge to this node, which can go back here, and also go here, and so on. Okay, so that doesn't really look like a linked list. It doesn't really look like a binary search tree. That's an example of a more general graph. Graphs are a really important data structure. The many algorithms in computer engineering and computer science are written to work on graphs because you can represent so many problems and so much data as a graph. If you want to learn more about it, this is the classic textbook for algorithms, which you can go find in the library or online. If you take ece297 next year, data structures and algorithms, you'll learn a lot more about them. But we're going to teach you some about them this course. Okay, so we're going to use a graph. And I said a graph has nodes, or vertices, and it has edges. So what should we make the vertices, what should we make the edges? Okay, it's a way of my organizing my street map. I want to organize it so that I can draw it, but even more importantly, we're going to write some algorithms later to find like travel directions and so on. And for that in particular, it becomes important. How did we organize this data in a graph? So what do you think the vertices should be? What do you think the edges should be? Whenever you're representing something as a graph, this is one of your questions. You know, like, well, what are the nodes? What are the edges? So what do you think? See if anyone has an idea on this. Somebody's got to have an idea. There's only so many options here. So I may have to resort to bribery. So after class, if you get this one right, or even close to right, come up, I'll give you a chocolate bar. So we'll see if that motivates anyone. Okay, so C14. First I got to ask a meta question. Were you motivated by the bribe or not?
Yes.
Okay, fine. Okay, so that's a vote for bribes, fair. What do you think? What should be the nodes?
The nodes should be intersections and the edges should be streets.
That makes sense. It makes sense to me. So, yeah. In this case, the logical thing to do, so come see me after class. Well done, thank you. Intersections are the nodes, and the edges are what we call street segments. Okay, so a street like Yonge Street actually goes through a lot of intersections. So it doesn't make sense to take a whole street and say it's an edge. What we want for our edges are what we call street segments. They're basically a city block worth of street, because that actually is what connects between intersections. Does that make sense to everybody? Okay, so now we've got our graph representation. So yeah, it's just a visualization of that. So we've got all these intersections, they turn into nodes, and we have, say, College Street here. We don't want to represent that whole thing as an edge. We represent a little piece of it, the piece that goes between 2 intersections, as a street segment. Okay, now we have to decide how do we identify these things. So we've got all these nodes. In Toronto, there are, I think I've got the numbers on here, but there's certainly 150,000 or so intersections. So how do we identify each vertex? We've got a few options. Okay, so one way we could do it is we could identify them all with a string, right? We could put some name on it saying, this is the corner of Yonge and Bathurst. Actually, it doesn't exist. This is the corner of Yonge and College. So that would work. But comparisons to strings are slower, and it takes more space to store a string. So we don't identify IDs or intersections with strings. What we do instead is we identify them with an integer ID. Okay, so every intersection in a city will be numbered. And we've actually chosen these numbers to be very convenient, okay? The numbers start at 0, and they go up to some number, the number of intersections in the city minus 1. Okay, how do you figure out how many intersections are in a city? Well, you call one of our API calls. So you can call this function getNumIntersections. For Toronto, it'll return about 190,000. And you now know, okay, the intersections are going to be numbered from 0 to about 190,000 minus 1. Okay, so on my little graph here, now I know I should refer to all these things with these integer IDs. We do also put a string name on these intersections, but that's really just for user output. You really want to work with the integer ID when you're doing most of your work with these intersections. Okay, so there are these names, and we basically name them based on the streets that intersect there. One of the reasons you want to do your work using these IDs is, well, integers are faster to work with than strings. They're smaller, they're easier to compare. Another reason you want to do it is we guarantee that all these IDs are unique. We will never give the same intersection the same ID. We probably don't use the same string, but we don't guarantee it. So that's another reason you should just use that for like output if you want it. Don't use it for your key decisions. Okay, how do we identify the edges, these various street segments? We use the exact same approach. Okay, so for Toronto, part of what we've done in our offline processing in that OSM to bin program was we worked out how many street segments are in Toronto, pieces of a road between intersections, and then we number them all. We number them from 0 to, again, you can call our API and ask how many street segments there are. So we number from 0 to that number. They're all unique, so we guarantee we'll never give the same ID to 2 different street segments. We don't bother putting a name on these, so you can't ask for a name. Okay, so every one of these street segments also has one of these small integer IDs. Something to be very careful of in your code. Notice these IDs overlap. Okay, so intersections start at 0 and go to about 190,000 for Toronto. Street segments start at 0 and go to about 280,000. So you've got to keep track in your code if you have an ID. What is this ID? Did I just get a street segment ID or an intersection ID? To help make this a little more clear, in the API you're talking to, the Streets Database API, one of those 2 APIs you're talking to, we use type defs. So does anybody know what this line of code does? What does a type def do? Have you ever seen a type def? Yeah, so I'm going to go to A09.
If I'm not mistaken, it basically redefines the name integer to whatever you want it to be called. So
Okay, so you're saying it just defines a name kind of thing, defines a synonym, is that right?
yeah.
So you're right. So this type def just says that we can use this new word, street segment IDX or street segment index, and it just means int. From the compiler's point of view, that's the same as writing int. We also have said we can also use this name intersection IDX, and from the compiler's point of view, that also means int. Okay, so what was the point of doing this? We could have just written int. We did this so that in our API, when you read what kind of variable are we expecting, this gives you a hint. It tells you what kind of index we want. Okay, so we have a function, for example, in that API that you're calling called getIntersectionName, and it takes an argument of type intersection IDX. And you know from reading this that that's just an integer. But it's a little bit more self-documenting, because we didn't just say it takes an integer. We told you it's an integer, but that integer should be a valid intersection index. When you're working in your code, don't write code like this. Okay? Don't say int my index. It'll work, right? It'll compile. It's not wrong from the compiler's point of view. You could pass this into one of our APIs and it will do what you want. But it's not very clear. One of your teammates is reading this code, or even you're reading it a couple weeks later. You may not remember, well, it's an index for what? Street segment, intersection, something else? So write it like this. Say I have an intersection index, which is really just an int, and I'm going to call it my intersection index. Okay, so that name is making it very clear. You know, this is for an intersection, and it's much less likely you're going to get confused. Your TA is going to be a lot happier with your code too. Your TA is not going to like this. And what about this? Should I say this? Int I. It depends. If it's a loop counter, maybe it's fine. But if this is a variable that is unclear exactly what is it, I is a terrible name. You know, a person probably goes, it sounds like an integer, but we've got a lot of integers flying around in this program. Give your teammates a better name than that. Try not to do that. Yeah, do you have a question?
So two questions actually. So first question is.
You got to say it really loud though, close to the mic.
Okay, so two questions. First question is like, so these functions that like the index functions that we've seen, those exist in the header files that were provided, that you provided for us, the low level,
yes.
high level.
So we have given what I'm showing you here. This is one of the functions in streets database API.h. Okay, one of the header files that we are giving you, okay. And it works. Okay, like we have written the C++ files, we have processed the data. This returns the right answer.
Okay, and we don't get to see the classes that we just like.
We don't give you the C++ code for that because you don't need it. Okay. First, that's actually one of the purposes of an API. That we can give you the interface, and if it's properly commented, you don't need to see the C++ code. Okay. So the C++ code actually is written, some of it is reasonably advanced. It might confuse you is the first thing. The second thing is occasionally students start trying to change it, which is chaos, because you can't change that code. It basically is written to work with our data.
So another question I have is like, so you changed the name, you redefined the int to be intersection IDX.
Yeah.
But so that it can be clear what we're working with. But then why can't we just like you have like int my intersect IDX? So
you're saying, what if you just did this? You're going to use the word int, but you're going to give it a good name. Yeah. Is that right? Yeah. That would be pretty good too. So that's not terrible. So if you did that, if you said int and then you give it a good name, your TA is probably reasonably happy. So if you do that, it's okay. We made these type defs because we think it's even cleaner, but you can make your judgment call on that one. Okay. Okay, there are different kinds of graphs. So first choice in a graph is always, what are the nodes, what are the edges? Second choice, what kind? Okay, so should it be undirected or directed? An undirected graph, the edges just say these two nodes are connected. In a directed graph, there's a direction, okay? So I've drawn it as arrows on the right. So this node can go, there is an edge going to the node to its right, but it can't go the other way, okay? So edges now have a direction. Which of these types do you think you should use for a street map? Directed or undirected? So let's see, I'm gonna go to A09 again. Whoop. Looks like I took C04. You jumped in first. So where's C04? What kind?
Directed.
Directed. Why do you want directed?
One-way streets.
One-way streets, yeah. So if we never had undirected, if we never had one-way streets, this would be fine, but we do. So you should use a directed graph. Okay, let me ask you another question though. There are two-way streets. How are we going to encode those?
Two arrows.
Right. So you can do two-way streets just by having two arrows. So this is the type of graph that we're working with. It's a directed graph. Okay, and you pass your driving test. You know about one-way streets. That's good. You're already in the top, 80% of drivers. Okay, so.
I didn't.
Okay, so some of the most important calls in the streets database API that we've given you are to figure out things about this graph. Okay, so you can ask, okay, so we have a bunch of different API calls. You're going to have to read the header file fairly carefully. You can come to the tutorial this week to see how do a bunch of these things work. But yeah, basically these 3 API calls that I've told you will help you figure out, okay, at this intersection, how many street segments are there connected to it? What are those street segments? And then I could get some properties about those street segments, about those edges. So see the header file for more detail. Each street segment has information about what is its from intersection and its to intersection. And it has a bool about whether it's one way or not. If it's one way, then you can only go from to. If it's not one way, then you can go either way. The from and to don't mean anything, they just mean the 2 endpoints. Okay, so there's a bunch of API calls in there, or a few API calls in there to essentially get information about the connectivity, the graph. But there's some more things. It's typical in graphs that you have extra information you annotate on the nodes and edges, and that's definitely true in this project as well. So on the intersections, I already told you we have this index that we use to identify it. We have a name. We also have where are they, and they're stored as a latitude and a longitude. The street segments, which are the edges, right? These pieces of a city, like a city block-sized piece of road. Again, it has an index that we use to identify it. It has a speed limit. It has a property of whether it's one way or not. And it has something called curve points. Okay, so not all city blocks are straight. Sometimes a street curves. If it's straight, we just need to know the from intersection and the to intersection, because those both have locations, latitude and longitude. That's enough. But to get the shape of a street that actually curves, we need more. So what we give you are something called curve points. We give you points along the street that tell you its shape. So not all street segments have that, but some do. And you can ask about that. And then the last thing the street segment has is it has another ID called the street index, and this tells you what street you're part of. Okay, we don't store the name of the street, we store, again, an ID. Everything's being done with IDs here. Okay, so let me show you first what curve points are. So if I have a street segment and it's perfectly straight, you can ask how many curve points are on this street segment, and you'll be told it's 0. Okay, so when you're trying to work with it, like work out how long it is, if you're trying to draw it, you just draw from it has a from intersection and a to intersection, so the 2 intersections at its end, and you just draw a straight line between it. That's all there is to it. If it has some more complicated path for that city block, when you ask how many curve points do you have, it won't be 0. So here, if you ask how many curve points are there, you'll be told it's 2. And you basically, the shape of the street starts at the from intersection and then goes through each of the curve points and ends at the to intersection. So with a bunch of curve points, we can pretty accurately model very curved streets. Okay, so those are the 2 most important things, intersections and street segments. But there are a few other items in this data as well. So one is streets. Okay, so Yonge Street. Yonge Street is made out of many street segments, right? It's many blocks long. Okay, so it's a group of street segments, and the way you figure out that basically each street segment can tell you, here's the ID of the street I belong to. So all of these street segments would give you the same ID when you ask, what is your street? And that street will have a unique index. So Yonge Street has a unique ID again. It again goes from 0 to some number. So you can ask how many streets are there, for example, in Toronto, we'll tell you, and you know all the street IDs will be between 0 and that number. It's also going to have a name. The name is not guaranteed to be unique because that's the way cities are. Okay, so in Toronto you'll have more than one main street because various towns grew together. So we're using the real street names, but don't assume they're unique. Last thing we put, well, actually the second last thing that we put in this API kind of more organized API for you, are points of interest. Points of interest are pretty simple. They again have a unique index, starts at 0. You can ask what's their location, and you can ask what is your name. So you can ask, for example, what's your name, and it might be Tim Hortons. And then the last thing in this simpler API that we're giving you is features. Okay, so features are basically outlines of interesting things that you might want to draw. So you can ask a feature, what is your type? And the answers can be things like lakes, parks, etc., ponds, buildings, stream, and so on. Okay, so again, the features all have an ID, starts at 0, goes to some maximum number. They have a type, and then they have a sequence of latitude and longitude points that basically define the shape of the feature. If the first location and the last location are exactly the same, then this is a polygon. Okay, so the outline of High Park, the outline of Grenadier Pond, these are going to be polygons. They're going to have the first location and the last location be the same when you ask, give me the list of all the points on your boundary. If they're not the same, it's what's called a polyline. A polyline is just a sequence of line segments that are each straight. So these, for example, streams within High Park will actually be polylines. Hopefully this all makes sense. And I know there's a lot of stuff. I'm basically giving you an overview. You have to look at the header files to get the details. Okay, so let me talk about how these two APIs fit together. So I've been describing this Streets Database API, this sort of higher level API we've given you. But I also told you there's this low level one, the OSM Database API as well, that you'll have to use a bit. Okay, so Streets Database API has intersections, street segments, features, and points of interest. They're all identified by small integer IDs, so approximately 0 to 250,000. OSM Database API the data is more raw. We've done less processing on it. It is what you find on the OSM wiki. It has, again, 3 kinds of entities. Those entities are OSM nodes, OSM ways, and OSM relations. The way our API works is it uses inheritance. So all of these things are an OSM entity, but so that's the base class, and then there are 3 subclasses, 3 subtypes. So again, a node is just a point. It's a latitude and longitude point. A way is a path, so it's a sequence of nodes. And a relation is some grouping of any one of these, any number of OSM nodes, ways, and even other relations. The way you can work with our API for this is you can ask how many OSM nodes are in Toronto, and we'll tell you it's about 9 million. And then you can loop over all of them asking, tell me about node 1, tell me about node 2, etc. But the main way that you identify the elements in this OSM database is by this 64-bit, huge, globally unique integer, okay, called an OSM ID. And that's a really big number. That means that number goes from 0 to about 10 to the 19th. So when you interact, you're going to find when you work with the OSM database API, which you have to do for a couple of functions, you're going to need to use these OSM IDs some, because that's how we're going to ask you questions, and they're big integers. These items, the Streets database elements that we've created for you, you can ask them questions with these smaller integers, these indices that we've given you. They also all know their OSM ID, so they can answer, if you ask a street segment, what is the OSM ID that you came from, it can answer that question. And that is how you can link these things, if you wish in later milestones, to the low-level OSM data. And in the comments in the OSM database API, it tells you actually exactly how do we make street segments, how do we make points of interest, how do we make intersections, etc. from the OSM data. You don't need to know the details of that for this milestone, but it's there in case you're curious and in case it's helpful in later milestones. So that is